We are going to close the doors. This meeting is supposed that you have read not well. It applies. Please read. Thank you very much to Dominic and Bill for the minute taker and JavaScript. Karsten, thank you very much. Well, this is the agenda for today. We are going to go fast to go directly to the points. Well, our milestone, we have 2 milestones for now. And now we are going to talk at the end about the charter. This is our active internet draft. This is our related internet draft. And there is one expired. Open tickets. And okay, this is going to present Michael. He's not here. Well, this is our cases, or we can, maybe because he was talking in 6 months as well, we can pass to the other presenter. Thank.
Just wanted to make one remark. We have lots of new drafts coming on, which are all personal. And we also have to discuss the charter where we have the milestones. So what we propose is that we will not post a question if this will be a working group item, but we will just go through them, have the different questions responded, and that at the end during the email to the mail on the mailing list, we will discuss if there is interest in the drafts and how we will continue them. Okay.
So you can just start. No, just go one back, please. Thanks. So this draft aims to collect several DIS-related modifications to improve the current operation of Ripple. This draft is actually quite old. It dates back, I think, a year now, and there were some affirmations on the mailing list, so I think people are interested in this. But of course, there is a lack of discussion, so I hope this will change today. So can you switch one? Just a short recap. The DIS message type of Ripple is used to request the DIOs, and the DIS header consists of 2 bytes. So we have 1 byte of flags, and we have 1 byte for, it's just reserved. And then, of course, you can include options into the DIS. If a node, any node in the network receives a DIS message, a unicast DIS message, then this node must reply with a one-shot or one-time DIO. And this one-shot DIO has to include a configuration, a DODEC configuration option. On the other hand, if you receive a multicast DIS, then the node has to reset the trickle timer, which again leads to trickle-induced, multiple trickle-induced propagations of multicast DIOs. So this is the current state of how it functions.
Rahul Jadhav, Huawei. The regular multicast DIO option, the no configuration option mentioned there is what? I mean, it's
yes.
A configuration option can still be sent as part of multicast DIO. So, right?
Yeah, it can be sent, but the draft, the RFC does not mandate that it should include a configuration option.
Right, but it can be sent.
Yeah, but it mandates for this case, for the unicast this case.
6550 already mandates it, or you want to mandate it?
No, 6550 mandates
already
that
mandate for unicast.
the configuration option is included in the unicast DIO. So in the context of this draft, several use cases were identified, and these use cases show that there is room for improvement in certain behaviors for the DIS-related behaviors. And we try to collect those behaviors. I mean, this is not a complete list of all behaviors. There are, of course, more, But this is why we encourage everyone to participate in discussions to find more behaviors that can be improved with the optimizations. And I mean, let's just talk about these behaviors. The first behavior is the multicast DIS, which triggers a trickle reset. So if we just assume we have a network consisting of a converged DODEC, it could be like shown here. And if there is a node that appears without prior knowledge of any parent before, then this node may want to use a multicast DIS to join the DODEC. And by using a multicast DIS, I mean, we just heard before, all nodes in the neighborhood that receive this multicast DIS will reset the trickle timer. And this leads to multiple trickle-induced DIOs disseminated in the network. So this will, of course, I mean, this has a really big impact on the network itself if all nodes start almost at the same time to disseminate multicast DIOs. And of course, this is multicasts. So if we have sleepy nodes, they will wake up. And this is not optimized for the IoT scenario. So this is our current behavior. What is actually desired is that we receive unicast DIOs instead of multicast DIOs directed to the node that wants to join the DODEC, like displayed here. And to come from this behavior to the new behavior, what we want, we proposed some improvements to the current DIS header. So we inserted 2 new flags, the N for no inconsistency and the T flag for DO type. Basically, if we just assume these both flags, it does not apply to the unicast DIS. And if the N flag is set to 0, it's the same behavior as before, so it's backwards compatible. But if we set, for example, the N flag to 1 and keeping the T flag 0, then we request a one-shot multicast DIO without resetting the trickle timer. This is the crucial point here. So we gain more control over whether we should reset or not reset the trickle timer. And then we have the case where we can set N and T to 1. And in this case, we again request a DIO. In this case, it's a unicast DIO without resetting the trickle timer. So just by introducing those both flags, we have a lot of control over what we want, what we don't want. And then we have a new option defined here. This is the response spreading option. And this is necessary for cases where we have a large density and we request DIOs from the neighborhood. And they will, of course, try to serve these DIOs simultaneously, because there is no, this is not trickle based. And to mitigate this, there is the spreading interval that the sender of the DIS can specify, so that all nodes try to randomly send these DIOs and not at the same time. So this is just to reduce the number of collisions if we have a large number of density, nodes. And then there's another behavior. This is the selective multicast DIS. So currently, the current behavior is as follows. We have the solicited information option, which is currently there, so we can use it, and we can reduce the number of nodes that want to respond to the DIS by filtering the instance ID, the DODEC ID, or the version number. But this is not enough. We actually want more configurability, and this. So what we actually want is the desired behavior on the right side of the slide, where we can even further restrict the number of nodes that should respond to the DIS. So, you can look at this picture. We have a multicast DIS that goes out in all directions, and only 2, for example, respond. And this is achieved by just using the metric container option, which is already present in the RIPL. This is nothing new. and just applying this to the DIS. Currently, it's only usable for DIOs and DAOs, but by using these for DISs, we can include certain routing constraints so that only those nodes answer that we want to answer. So for example, nodes with better link quality.
Rahul Jadhav, Huawei. The multicast DIS message that is sent out here, it solicits for a unicast DIO. That's the proposition, right?
Yes, yes.
But in certain cases, for example, when the complete network starts up at the same time, maybe multicast DIO might make more sense there. So can it be something like, during we wait for the response spreading option, if we receive, a DIS which is above some threshold, then we can still multicast the DIO.
This is possible because we have these flags like defined before, right? So you can just apply those flags and say, okay, we want multicast DIOs or multicast unicast DIOs here.
Pascal Thubert, this is actually very linked to a question I have. Some of your bits, I really agree with what you want to do, and I will support the adoption of your work. My question here is that you are actually giving the control on the devices where the control should probably be on the network side. And this question that we just asked get about whether the network is booting or not. How can an individual device know? How can an individual device know about the size of the network? These are informations which may flow and that the nodes which are already in the network may know because of configuration options and things like that. But a joining node which has no configuration option and no idea about the size of the network, etc., how could it possibly send those bits? So I agree with what you're doing. Probably the location of those bits can be discussed. And who is in control? I think the network should be in control, not the end device.
Sorry, I can't switch to my. Can you feed my? In case a network is operated by
We should say.
Yes. Okay, so we got from Dominique Bartel here for the note takers, and that's probably you are, that in case the network is operated by an operator, the device will know whether it's initial boot and the size of the network and everything because it will be provisioned prior to deployment. So he knows about density plans and everything.
Another 2 minutes, please. Yeah.
Okay, so then let's go on. We have another.
But Dominique, just Pascal here. The network would know as well. So a solution which is network-based would work in both cases. Fair enough? Fair enough.
So to go on, we have another behavior, which is the inflation of unicast DIOs. So basically, like we said before, if a unicast DIO is requested, then this unicast DIO must include, and this is really a must in the spec, must include the DODEC configuration option. But this is actually not necessary every time. The configuration option is depicted here, and this is basically static information. This will mostly never change. But if we try to request unicast DIO, this will be inserted every time, and this is just 16 bytes of superfluous data. So this is why we try to, as a desired behavior, to make it more configurable, what we want to request and what not. And for this, we have another option for the DIS, which is called the DO option request option. So basically, the DIS can request an option from the next DIO. And this is also a good idea because this does not only apply to the DODEC configuration option, but you can also request, for example, prefix information options, or you can request 6 COs, which is not possible with the current spec. So we have with this option pretty more flexibility, and we can include this option, of course, multiple times in DIS to request multiple options at the same time. And for this, to be backwards compatible, we need another flag from the DIS, which basically says if this flag is set, then don't send the DODEC configuration option in the unicast DIO. And if this flag is set, then take the new behavior where you just put the configuration, the option in the DIO that's requested. And if the flag is not set, so the default behavior, then just put the configuration option in the DIO option.
Okay.
Well, what about the time?
You're done.
I'm done. So yeah, really fast, here's just one summary slide. So basically we have 3 new flags for the DIS. We have 2 new options, the response spreading option, the DIO option request option, and we want to allow the metric container inside of the DIS. And of course, we want to stay backwards compatible. This is why we use all those flags.
Okay.
The question at the end with the charter discussion. Thank you.
Okay,
Okay, great.
thank you.
Thank you.
Next one.
Michael?
One additional comment, Emmanuel Bocelli. I think there's more or less up-to-date implementation of that in Riot, just for those people who want to play with the current things.
Oh, thank you. Okay.
There's no
No, there is no pink box.
there's no pink box,
No,
Oh, but you are on focus.
there is
Okay.
an imaginary one which you.
which is over here.
No,
No,
it's not
where
there.
you are, it's okay.
You're focused at this moment. Please stay there.
Does that really work?
When?
Yeah.
Did I point it this way?
No, you did it.
I can move, don't worry.
Okay.
I think I switched.
Huh?
I think I switched off.
Oh,
There's a switch on the side.
The expert.
thank you.
It's red for on and green for off.
Otherwise, we can do it for you.
Okay, well, so let's go to the first slide. Okay, so Inez and I have a document that we discussed last year that is attempt to clarify when you need to use IP headers and when you do not need to use IP headers, and when you need to add the RPI hop-by-hop option, and when you can remove it, and when also you add the RH3 extension header. And I'm going to tell you, actually, it was only last week that I clued in that one was an extension header and the other one was a hop-by-hop option, which is in the options header, which is a very precise little bit, which turns out to be important to know. And so we had a document called Use of RPL Info, which we kind of had hoped would actually we would be done in March, and we would publish, and it would establish the requirements for what you actually need to do in the data plane, which RFC 6550 was a little bit vague about, and furthermore that what the inputs to Pascal's work on compressing is. In other words, he can't really optimize the compression correctly if he doesn't know what the goals are. So, as is normally the case in the IETF, the assumptions change as you work. So the 6-man has, please stay there, yeah. Is it me? So you're doing this, okay? I'm not touching the buttons, unless I am, and I don't know. So 6-man had a large, I'm going to say flame war, in the last few months over revising 2460 BIS and whether or not this would permit in the future people to insert extension headers and delete them not at the end nodes or not in a packet addressed to you. And so after all that discussion, they added this note that essentially says that intermediate nodes essentially are expected to ignore the hop-by-hop option unless they've been configured not to. And this essentially reflects the reality, apparently, that most silicon out there has been ignoring it for some years or decades, and is not likely to change. Go
If I
ahead.
may add, Michael, that's Pascal. We mean router silicon. So the original text
Yes.
in 2460 was dealing with routers, and it's important for us that we talk about hosts here.
Right, and it says all nodes. It doesn't say routers here. It says all nodes. It's really important to us. Okay, so we expect that end hosts, unless they have been configured to pay attention to hop-by-hop options, they will ignore them. They will not examine any of them. And so specifically, that means that they will not look at inside the hop-by-hop option and see the RPI option, which they don't understand, and therefore drop the packet, because our RPI option has been marked as, if you do not understand it, please drop the packet. Okay, and that was a 2460. Now, they have not agreed to change the text around that. So the question is, a node that has been configured to examine a hop-by-hop option, which has not then been told that it knows about the RPI option, could well drop it according to the current text. I believe that that's something that 6-man should clarify, but that's not, we're not going to get there. So next slide. So they kept this text, and we argued yesterday about the second paragraph, and let's just go on to the next part. They still, you cannot insert or delete an extension header, such as an RH3 midway. So if you want to remove an extension header, then the packet had better be one you created or one that was addressed to you. Okay, next slide. So prior to this, let's see if we can do it. Can I go to the next slide? Yeah, so just stick here for a moment. I'll explain the slide, and then we're going to jump through this because it's a form of animation here. Go ahead.
Can you go back to previous slide, please? Actually, the one with the 2 pieces of text from 2460. The first
Pascal, is it?
Yes, Pascal. Yeah, again, the first paragraph is really saying that PMTU discovery is hurt.
Yes.
By this, doesn't say you cannot do it. Right. That's all the wording game which is happening.
That's why we were having such an argument yesterday.
Yeah. So we are still inserting headers so far. Right. It's not like we can't. Well, somebody will say you can't.
I do not believe that there's a consensus for your interpretation, but let's continue on anyway. I would like that to be the interpretation, but I don't.
The only consensus is that 2460 will not change. The BS will not change the game that is already set in 2460. Right.
I see. Next 2 slides ahead, please. Okay, so we have a DAG here. Nodes are labeled, and we are trying to send in storing mode from F to G. And we know a priori, don't ask how for the moment, that G is not a ripple capable node. So it is a classic 6LN, which speaks neighbor discovery or something like this, and for some reason does not participate in ripple, does not speak messages, has joined the mesh because E has heard its neighbor discovery, it's NA, and has sent a DAO up on its behalf. Okay, and
the English word is host.
Yes, correct. It is a host. That is. Thank you very much if you like to say that. And the how do we know? Well, it's also possible that E has set the E flag in the DAO, but that would propagate upwards to B, and we don't know at this point whether B would tell anybody about whether or not G was a node. And if someone can say whether what implementations do versus what 6550 says, I think it's completely, there's no actual text to specify it. But even if B did propagate that buck up to A, F sure doesn't know. So we're going to assume for the moment that somehow F knows about it. So he's going to send a packet, and he has no choice. He has to send an IP header to D. Next slide. And D is going to take it off. It's going to add a new one. The new one is going to be addressed to B with an RPI, changing the rank at each time. Next slide. B is going to take it off and add a new IP header, which is going to be to E. And we can discuss whether these are link local addresses or global addresses that it uses. Next slide. And then E is going to receive it. Notice the outer address is his address. So he has the right to remove these things. It's going to remove them. And next slide. And then G receives a packet he can understand containing no headers that are weird and unruly. Okay, so that was the situation before. So next slide. So we do the same thing, assuming this new 2460 text. Okay, next slide. Okay, so F can send this packet. He sets the RPL rank as 4. He addresses it to G, sends it up. Go next slide. R is decremented, sends it up, continue. R is decremented again. Next slide, go forward. Oh, there we go. Goes 3, rank is increasing now. Next one, and G receives it. G doesn't know anything about hop-by-hop options, has not been told to examine it, happily ignores that extra thing, and everyone is happy. You have a Dawn, please say something.
Don Sturry, Silver Spring Network. So I'm curious, what DAO option did E use to tell anybody about G?
But we agreed not to discuss that.
The answer is there is one bit in which says external. So it's just you set the external route in the DAO. That's all.
Oh, so E.
So it was designed for it. It's just that ripples. We said we don't support G today in 6550.
Right.
It's just not supported.
Right.
But
so
we prepared for it by having an external bit.
we just
somewhere.
didn't tell you how to propagate the E bit, and we also didn't make it clear how in the world F would find out, because F is not in the upward path of there. Okay. So in the absence of that knowledge that G was incapable, F would have to pessimistically always IP header L the traffic, unless it was sure that there were no nodes like G. So we could have gathered all the E bits at A, and if they were all 0, we could have added a message to our DIOs saying you live in a hostless DODAG, and therefore you don't have to do this. So with this text with 2460, we can actually go back to what I think everyone originally thought storing mode would look like, which is you put an RPI header hop by hop option in, and you send your packet and everyone's happy. So isn't this a big improvement? We should really send like birthday cakes to 6-man people or something. So thank you cards.
So Don Sturry, one other thing. So F, no matter who it was sending to, it has to have some information that destination is a member of this Ripple instance, and in a lot of cases it doesn't, because some other PAN could be using the same prefix and coordinating addresses across different PANs.
So in the document, okay, we distinguish the case of F is sending within the DODAG on the assumption that we can say, if you're essentially within the /64, then you're probably within the DODAG, and if you're not within the /64, you're probably outside.
No, but that's a bad assumption, because
please argue that point on the list, because I would like to have that argument. I don't know if it's a good assumption, but we made that assumption.
So here's a different deployment. You could have another entire LBR tree over on the left,
right,
and somebody above it might be coordinating the use of a single prefix,
right,
and allocating addresses in a coherent way, and F has no clue that that's going on.
Agreed. And in that context, before 2460 BIS, we would have to then pessimistically IP header everything. Right.
Correct.
So it's good for the case where we send traffic out of the DODAG as well.
Yep.
Right.
Yep.
Okay. And the example that you gave of coordination, well, that's exactly Pascal's backbone router scenario.
Right. Exactly.
Right. Exactly. So I agree with you completely. Okay. Right. But there are some also assumption that within that /64 of coordinated LLNs, that probably all of those devices were probably Ripple capable, and therefore could ignore the RPI. That may be a bad assumption, but you could make that assumption and say, oh, well, but it works because I assume everybody who's part of the backbone of LLNs is knowledgeable that they're part of the backbone. Right. But in any case, with this change, we don't care. And this is great news for storing mode. Okay. Can you go on to the next slide? Storing mode with the inclusion. Okay. We have another example. I'm going to go really quickly here. So this is an example of the host sending a packet into the DODAG. So it goes up. Okay. We have no choice. We have to add an IP header. Okay. Now, hang on. We have to add it hop by hop, because it's the only way to do it. We're adding it hop by hop. Go on. Can you go? Okay, go down. So it's B to D. D, it's addressed to D. Go back one. It's addressed to D. D can remove it. Okay. And go on to send the packet on, or whether it removes it or not. In fact, it didn't have to, because D could remove it, because you know what? It's this weird thing. Why am I receiving this IP header? But F should be able to cope with it. We wrote it as it removed it. Okay. Next slide. So with the inclusion, it looks a bit different. Okay, we didn't do all the steps here. With the inclusion, it means that E adds it, but note how E now, does this work? Can I do this? I know remote people can't see it. It's on. That's on. Well, that's really confusing. So you notice there's an F here, whereas before it said B. So that means that we're not actually having to rip the packet on and off each time. Okay, we add the header, we added it once, we had no choice because the original didn't know to add it, and now it flows all the way to there, and we're good. The inner packet is G to F, that's E to F. A little bit weird because F has no idea why E is sending him a packet. There's some ACL issues. This does really matter when a host here is sending out to the internet. That's really weird. Oh, I was expecting traffic from G and I got traffic from E. But inside of that, I found traffic I like. And I'm not aware of any desktop operating system that doesn't freak out about that, but they perhaps that's an issue. Next slide. Non-storing node mode. Next slide. So non-storing node, again, we have this, we magically know that it's not a member. Next slide. And because we added an IP header with an RPI. So we're going up the DODAG. Next slide. We're going up again. Next slide. So now at the top, we took off the one that we got on the way up. So go back actually one slide. Notice you notice this is addressed to A. Okay. He knew that he knew that he had to add this header. He knew that the root had to take it off, and therefore addressed it to the root. And he knows who the root is because that's the DODAG ID. Next slide. So the root took it off. He readdressed it to E. In non-storing mode, we knew, because the root knows everything about everything, he knows that G is connected to E, and we can use the E bit quite intelligently there. And so he knows that he has to address it to E. Rank is 1. He adds the RH3 that contains the thing. Next slide. Next slide. And so then E, it's addressed to him, rips off these things, winds up with this thing, and we're good. Okay. So it's actually, well, that's without the RFC 24, the BIS change. So next slide. So with the inclusion, it's the same. There's no change. Okay. So from a not RPL leaf, go on. So there's no change for non-storing mode. This doesn't help us in non-storing mode, but non-storing mode is already a relatively easy case, or was relatively tractable, and we could know. We always had to send it to the root. Also, the question of F, does he have to IP encapsulate or not? Well, he doesn't know. So again, F would benefit from knowing if there were never any hosts in the network, he would never have to do that. He could always put the RPI in. So here we have this guy sends a packet. Next slide. This guy has to add a IP to add the RPI. Next slide. Goes up. Okay. So he receives this E to A. He receives this packet. He rips off this stuff. I try to make different colors. And he adds an IP packet with an RH3. So it's addressed to B. Next hop is D. And it gets consumed. And the packet gets removed. Now, you don't have to remove it at D. We could leave it all on because F is there. And that's a choice. I don't know if there's a clear implementation one way or the other about whether you want a source route to D and then F, or whether you want a source route to D and then next hop to F, right? I'm not actually sure I'm not sure it matters, except that you might as well rip off the headers that you don't need as soon as you don't need them. Okay. Questions on this? We have some benefit. We still can't remove RH3 headers unless we interpret the text 2460 very promiscuously. We can't remove the RH3 header at the root. We can't insert it. We have to address things properly. So in the original text, in the original description, we described these need to putting in an IP header that travels from one hop to the other. So in the original set of slides, you saw that it changed each time. It was removed by each node and added by each time. I have a real problem explaining that to myself. I'm wondering if anyone can help us explain it, okay? Because I know what I'm talking about, but I can't explain it. So if you can explain it better there. And then we have the E flag. Do we want to write some text that makes it clear the E flag is supposed to propagate up, that it should be set for hosts? And then the question is, should the zeroness of it, the universal zeroness of it, be announced back to all the nodes in the DIOs, saying you live in a pure Ripple an environment and you don't need IPs.
Mike, can you go back to one? This is Don Sturck again.
Yeah.
Sorry. Yeah. How would you use linked local addresses here?
Well, you're going from one hop to your parent. And so you could address your parent by his link local address or in the packet, or you could address it by his global address.
So this is in the outer
Outer.
IP?
Outer.
So I still don't see how you'd use linked local address. It has to be something routable, right?
No. Go back and just go back to the slide where I think it's get back to storing. Yeah, back to there. Go back. Okay, no, forward one or a couple, or you went too far.
Where?
That, the next one, the next slide. Okay, there, no, back one. There.
This one?
Maybe I can do it myself.
Oh, yeah.
Oh, it works.
That was not the right one. Okay, B to D. All right, so in this case, right, in this,
E to B.
okay, so in this case we have E to B, right? So this is a link. This is a single link, and this is a single link. So B has to rip off that other outer header, and has to add his own. I mean, reality is we all know we're just going to overwrite the bytes and pretend we took it off and added it, but never
I think
mind
it's just
that.
an artifact of the way you drew this. If you added one more hop in between B and D and B and E, I don't think link locals work anymore.
No, but then B would have to send it to that intermediate hop. Okay. These are single link, single hop radio.
So
links.
you're D. Okay. All right.
Okay. If you make your thing more complicated, then we just have to change the rename number it. The point is that B and D. So this B could be B's global address or B's link local address. And I think the advantage about using the link local address is that now it compresses against the MAC address, the 2-byte MAC address, versus the potentially longer one, which may also compress just as well. So I'm not sure. Like I suspect it may not matter. But I think we should write something specific down so that people don't have to have 2 code paths or something like this, or more than 18.
Michael, can you conclude?
Yeah, I'm done.
Oh, good. One question.
I was just a clarifying point, Pascal, here. Some devices may have more than one radio, and it's very possible that D doesn't know a global address for B. So using link local is safe in any case.
That's a good point. And he knows that because he got the DAO from his link local address. Yeah, that's a good point. Thank you.
Okay, thank you. Karsten.
Thank you. At some point, I need to find a student to find out why people switch off things. I don't know.
Energy saving.
Energy. Okay, good. This is a set of slides that I have not shown on IETF 91 because it fell off the end of the agenda, but that I have privately shown to a lot of people. So it may look familiar to you. And at IETF 92, I actually showed it inside 6LO, I think. I'm sorry, the original authors are still here. So right now the co-authors on the draft are Hao Chen and Olaf. Can you just wave? You can wave too. Okay, thank you. So Ripple has multicast, but only for storing mode. And you know, I'm of the personal belief that storing mode doesn't exist. So for us, it was very interesting to see, can we make this happen for non-storing mode as well? So in storing mode, we have these multicast DAOs, which create for each multicast address state in the entire network, in the path upwards to who is subscribed. This creates breadcrumbs. And yeah, has anybody implemented that? I have no idea. I haven't seen it yet. I haven't tested it yet. So it's specified, but it's just as the entire storing mode, it's not really there. So how do we do this for non-storing mode? Non-storing needs source routing. Now, source routing multicast sounds like, how do you do that? So do you list all your outgoing interfaces? We somehow need to get to a situation, first of all, where the sender sends something, and then we find the way down towards the listener. In this picture, there's only one listener. Of course, there are multiple listeners, and that's really the problem, because source routing would mean that you need to enumerate all the forwarders that are needed. So in this case, it's only 2, but in other cases, maybe many. So how do we do this? We could do a list of the 16-byte IPv6 addresses for all the forwarders, but in a network that has more than a few members for multicast, that wouldn't work, even with the compression we now have for those addresses. It gets pretty big pretty fast. So in IETF91, the beer working group was built in above, and the idea here is that we do bit indexed explicit replication. So essentially, they also have a source route that is embedded in every multicast packet, and the source route actually enumerates the outgoing interfaces of all forwarders after having done a numbering step, which is left as an exercise to the reader, for all routers in the network. And well, that might even work. I think Pascal believes he can make it work, but it's a little bit difficult in the kinds of networks that we are using. So we try to look at using this kind of bitmap-based source route without having to have a stable numbering of all the forwarding routers in the network. And what's the answer? The answer, of course, is a Bloom filter. So who in this room knows what a Bloom filter is? Oh, good.
Yeah.
So a Bloom filter is a compact representation of a match-non-match decision for elements in a large set. It originally was used for things like spell checkers. So you had a compact representation of the set of words. It's done by hashing the element that you want to match with multiple hash functions, set a bit for each of the results of the hash functions, and then see if all corresponding bits are set. And this stuff is so old, it's out of patent. The idea is to send a Bloom filter with every package, and the various forwarders look at their outgoing interfaces, hash those using the set of hash functions that we have agreed on, and see whether all of their bits are actually set. And only if all these bits are set, the packet is forwarded. Of course, Bloom filters have false positives because hash functions are hash functions. They are not precise. What happens is you get spurious transmissions. And now we have to find out how bad is that. So if this guy, for some reason, has the hash functions pointing to bits that have been set for the other people, then we get a spurious transmission here, and we waste energy. So how bad are these spurious transmissions? First of all, they have no influence on correctness. So that there is no semantic damage. We just have more packets than you would like to have. So we have to find out what is the false positive rate and what is actually the density. So how often is the fact that a false positive exists actually being exercised in the network. And actually we can live with a significant percentage. So 10 or 20% overhead is fine if we actually manage to save 10 or 20% packet size. So false positives are not necessarily a bad thing. So we looked at the numbers here. The numbers here, this counts forwarders. So the Ripple ideology may be that every node is also a router, but in many networks we have hosts. So this doesn't count hosts, only nodes that would be potential forwarders of packets, nodes that have children. So with a 64-bit field, we get somewhat reasonable false positives up to, say, 20 nodes. So this is probability of 5%, 10%, 30%. I think 30% is a little bit, we should stop using this there. So that's 8 bytes, that's 16 bytes, that's one IPv6 address, and this is 2 IPv6 addresses. So we can do something like 100 forwarders in a network with a reasonably sized source word field. So how does the protocol look like? Well, we do need some DAO kind of thing, because listeners still have to indicate the interest. So we invented something called MLAOs, multicast listener address options, that can be sent upwards, and they're like everything, they are sent to the root, because the root's the only node that needs to know about things, which is the nice things about non-story mode. The submission phase of a multicast, so the phase where the multicast goes up the root, this is just tunneling. And the deliver phase is done by the root adding a Bloom filter in a routing header 4711, I don't know. And well, with what we know now, we might want to use something like a 6-low routing header for that. But at the time when we wrote this, we were just doing the normal thing with the IP and IP header and the routing header. So that's it. We implemented this 3 years ago in Contiki, which is interesting because Contiki only has story mode. So we first hacked in non-story mode and then hacked in this. And one interesting observation is that the forwarders actually can compute their hash functions once. They don't need to do this on every packet, which would still be reasonably efficient, but they actually can compute those once. And the root can easily insert a new member in a group, but it's hard to delete out of Bloom filter. I know that there are ways to have Bloom filters with deletion, but they kind of negate the benefits here. So this means if somebody actually leaves a group, the root has to completely recompute the Bloom filter, or work with a little bit of additional spurious transmission for a while. So it doesn't have to do it every single time. But after a certain amount of time, it's time to recompute that thing.
Rahul Jadhav, Huawei. For the Bloom filters to work, now the set of hash functions has to be standardized so that the implementations have to interop, right? So the set of hash functions standardization is kind of, I'm not sure if there exists such kind of, because the hash functions can be absolutely anything. And
yes, so obviously you don't want to have 20 hash functions. So the best way to solve this is to have a hash function with a parameter that you can step through multiple values. And if the hash function is really good, then you can just put this parameter in the first byte of the thing you're hashing and so on. So we don't really need many hash functions, only at the theoretical level. But we have to standardize which one we are using. So which one did we use, Olaf? Do you remember that?
I'm pretty sure it was SHA-256.
So in line to that, I have another question. I tried to search this OpenSearch implementation, but I couldn't find it. I wanted to specifically check the hash function used and whether it can satisfy the property, given the density of nodes, given the size of the network, given the number of hops, the hash function might vary. Even the dimension of the set of the Bloom filter might vary. So
we have a few too many knobs at the moment. So we have to reduce the number of knobs. So yes, it's true. The current draft doesn't tell you which hash function is being used, if I remember correctly. We don't need a cryptographic hash function. I mean, you may have SHA-256 in your node already, so it may be convenient to call that. But that's, of course, more expensive than doing one of the computer science hash functions. Yeah, we can find out. I think the next step would be to run simulation or another form of evaluation with different hash functions, and we probably won't find a big difference. We did something like this on the back of an envelope already and didn't really find a lot of difference. But I think this could be done a little bit more systematically, and then we decide for one.
Hold a second. So sorry, I didn't quite get the statistics in terms of, let's say you have 200 links. How many bits?
Forwarders. The interesting number here is the number of forwarders, the number of nodes that could be forwarding your multicast.
Right, but I thought that you're making the decision for every downstream link, right? Or you do make it only once and you...
For every outgoing interface.
That's what I meant, yeah. So
that's not a... Okay, depending on how you define your link, yes.
Yeah, okay. That's kind of the order, right? So let's say we have 200 of these outgoing interfaces.
Yes.
In the topology. So how many bits did you want to put in the header for the different, I mean, how many different hash functions? But that's the number of bits, right?
No. You design this in such a way that you fill the bitmap on average about half.
Right.
So if you have 256 bits and you want to fill it in half on average, then you multiply your average number of forwarders with the hash functions and get 128.
So if I have 256 outgoing interfaces in my network, I would...
That's not quite the figure. I mean, to get a false positive, the packet actually needs to reach you.
Sure.
So we are not counting all the forwarders in the network. We are counting all the forwarders in the network that already get the packet. So that are either on tree or happen to be in radio range of something that's on tree.
Okay, but just very simple example. I don't know upfront what my likely population is, right? So I have 256 outgoing links, and then I would roughly need 512 bits to represent that. Is that
simplified here? We're looking, Emmanuel Baccelli, we're looking at a case where there's just like one interface physically. So maybe you wireless, and so there's just like maybe we're looking at the one single interface cases, right? We're not looking at like
every single router usually has one outgoing interface.
Yes, but so you don't have like 1,000.
Okay, so in your example topology, you had something like 10, right? 10, 15, if I counted that correctly. Just
yeah. Okay, in this case, we have more like 3. Because these guys are out of radio range of the finger. This guy is in radio range. And if he actually gets that, then he will forward it. They are not numbered. We are just using the IP address of the outgoing interface and put that into the Bloom filter.
Sure.
But when we look at the number of false positives, really the interesting number is not the total number of things that could be in there, but the things that are in there, and compared to the things that actually have to make the decision.
But if I have different distribution trees, right? I have some that need to go to these 3 boxes, others to the other boxes, then I need to upfront design the number of bits, meaning the number of Bloom filters, so that I can support all of them, true?
Let's say you have a very dense network and you have a multicast group that gets to 80% of all receivers.
Right.
Then you will have a lot of false positives. But then you don't care, because with 80% forwarders and the dense network, everybody is getting the packets already.
So for this network, what would be the number of bits in the Bloom filter that I would roughly want to use if I don't upfront know what subset that I'm pretty good, whatever the distribution tree is, however, what the subset of receivers is. If I don't know that upfront,
there is potential for vendor differentiation here.
Okay, so I'm sorry if I'm standing here very long, but I'm trying to come up, with a very simple answer to what I was thinking was a very simple question, which is give me an idea about the number of bits in the Bloom filter, as little as I know upfront.
Well, we have 3 cases here: 64, 128, and 256.
Sorry, but we are running out of time. Please send that in the mailing list. 1 minute more or 2 minutes more? Okay, one quick question.
Olaf Bergman. These numbers are the theoretical probability of collisions. Like Karsten said, if you have a dense network, you could get this number of these p-values for having collisions in your Bloom filter. If your network is very wide, then you probably get lower probability of having collisions in the Bloom filter. So that's the important point to get here.
Pascal, do you want to make your point?
Yeah.
Okay, Pascal Thubert. So there are a number of decisions which can be made individually. One of them is to use Bloom versus bits, which is like having some elasticity with Bloom and hard-coded number of devices with bits. The second decision, which is more interesting, is indicating an outgoing interface of a router versus indicating a destination. You could also make this choice. Like in beer, classically, we have bits per destination, and we can use Bloom filters per destination as well.
In beer, we have egress interfaces, not destinations. But that would work for storing mode, but it wouldn't work for non-storing mode. For non-storing mode, we really have to do source mode.
Yes, right. So with your format, you indicate path, really, and the tree where beer could, well.
Let's take that off.
I really would love to see some discussions on the mailing list here. Thank you very much.
Thank you, Karsten. Thank you, Karsten. Next, Raúl. Oh, let me. Yeah. Peter. Sorry. Peter.
It should be easier. Okay. What I want to talk about is when you have a network where Ripple works, we also have Mipple, and Mipple is used for multicast. Now, if you have very dense network, as I'm trying to show here, where the left side reaches the middle and the middle reaches the end, but lots more, then if all the nodes actually do Mipple forwarding, you will get lots of messages. So it will be nicer if in the case that you want to use Mipple, that the number of forwarders are limited, so that you only have 2 forwarders which are reachable by every node, such that it can be forwarded. In this simple example, the nodes to the left will each reach each other, reach 2 forwarders, and the forwarders will put it forward. So the number of forwarders which you want to use, which can be reached, is dependent on the reliability what you want, and here I have set that to 2. That is what I want to see, that an algorithm which automatically selects those forwarders dependent on the configuration you have. The assumption is that the configuration is relatively stable, so it doesn't change every 5 seconds completely, for example. So what we do, that we have, so the work has been inspired by the neighborhood discovery work and by the simple multicast forwarding work, which is there. So you may not completely recognize it, but it is there. So the nodes, what they do is the data. So when you know the data, you know the algorithm. People say, so they have a state, so they are either the forwarder and potential forwarder. No forwarder of the one-hop neighbors, so all the neighbors, and the RSSI in and out to the neighbors to determine if you have a stable channel. And they have the set of 2-hop neighbors. Yeah, so that's a split. So what is the protocol? So the nodes link local multicast. They use Trickle for this. To the info about the one-hop neighbors. And what do they info? Their information, which is again just the address of the neighbor, RSSI of the lake, the number of forwarder neighbors that they have at the monument, and the number of under, which is the number of neighbors that they see, where the number of forwarders that those neighbors see are available. So you can see if all the forwarders have if all the neighbors have 2 forwarders visible, you will see that n under is equal to the total. And the state. The address of the neighbor is to select which one will change the state. So it is to break symmetries. We use in the message, I use CBOR format. I only use messages from valid neighbors, which is possible because when I can look at the RSSI in and the RSSI out. There are protocols dependently for that you can separate it out if you like, but for the moment I've left it in. And on message for the message, an update a node and execute the selection algorithm. So what is the selection algorithm? You order the neighbors on the NR under. So how many? So the neighbors see how many neighbors have the right number of neighbors, forwarders that they see, and you select the order on that on the address, and then the first neighbor has a value. Yeah, okay. So if you personally are the one with the largest NR under and also the largest max address, you make the selection that you state to FF if there are not enough forwarders. It's difficult to oversee. I did simulations to see what goes on. So what is the state of the draft? I've written this all down. I tried to simulate it. It looks reasonably positive. I mean, I had 3 forwarders in the example, but you said instead of the 2, and not exactly at the place that I wanted. So it looks forward, but I also had some errors. The stability criterion to determine that the NR under values are correct and not moving all the time, I don't know yet. I have to look at that in more precision. And I still have to look at what happens if nodes go away. And so you can see that you have a number of fast forwarders, you've selected it, but it goes away. So what are you going to do about it? And that's it. So that's all I wanted to say. It's just to draw your attention. I hope that some people are interested and that we can continue working on that. Any remarks? I was fast, I think.
Okay, thank you very much, Peter.
Justin Dean, I'm chair of the MANA working group. It was nice to see that this was inspired by work pieces we did in the MANA working group. I don't know if you were in, we just presented in the MANA working group about redoing the multicast forwarding information base for MANA networks. So we're trying to build pieces that other algorithms might be able to take advantage of in terms of deciding whether to forward or not, or do more complex things with multicast. So if you're interested in that, please talk. I would love to talk to you about your work here and see how it could work together.
I'm certainly interested, and also the efficiency of separating those algorithms up is also an interesting aspect. Yeah.
Okay, thank you. No more questions?
No.
Thank you very much, Peter. Next presenter.
Thank you.
Charlie.
Okay. Works. Good. Okay. Hi, I'm Charlie Perkins. I'm here to present a proposal for doing AODV in Ripple networks. AODV is ad hoc distance vector, ad hoc on-demand distance vector protocol. It's been developed for a good while. It has good characteristics for scalability, and so there was a previous proposal for doing peer-to-peer networking in Ripple networks, and it seems that AODV would do a pretty good job of that. And in addition to doing point-to-point, there was a draft from Pascal that talked about what do you do if you have a network of devices where the communication is bidirectional, but it's not symmetric. And so what we have here is a proposal for doing an AODV style route request, route reply, peer-to-peer route discovery in a network that has these kind of bidirectional but asymmetric links. So you might view this as an extension of RSC 6997, and hopefully if there's interest in the group, we would like to continue developing it. I think it would fit well. Support for storing mode. And so actually on this point, I'm curious to find out, maybe not just right now, but I'd really like to find out what is the proportion of Ripple networks that do storing mode versus non-storing mode. If I can just say for a few seconds, I always thought that transmitting bytes over the air for wireless devices with low power was really bad, and it was better to have a little bit of extra storage and do a little extra computation to save transmission over the air. So if that's not true, that's an interesting design point to know about. So as I mentioned, we want to support both symmetrical and asymmetrical bidirectional links, and in order to reduce the number of bits going over the air for non-storing mode, we'd like to avoid having to carry the address vector for that. So we have designed this to use a new mode of operation, and the new mode of operation allows the insertion of the route request and route reply messages. Okay, so this is pretty much what you would expect, but we have, since it can be asymmetric, That means that if you have a route from source to the destination, the route backwards could be different. And this is crucially dependent upon that this, although it is asymmetric, it's still bidirectional links are available. So what we specify is essentially that these DAGs are paired so that there's a way to go from the source to the destination and a paired way to go from the destination back to the source. So this is two instances, the route request instance and the route reply instance. The route request instance has this DIO with the route request option, and that's what the originating node, the source, sends out the control signaling. Target node receives it, and then once the target node receives that, that means that the target node has a way to send packets back to the originating node. Plus, it means that the target node is going to send out this route reply option to enable the originating node to get a good route back to the target node. And that's, it says down here, that means that the target node is sending out control signaling to the source of the route request, and that gives the originating node a way to get back to the target node. Here's a picture of exactly what I just said. And we'd like to have it to be the case to support symmetric routes, which means that if you have a set of links that offer a route from the source to the destination, then the destination can just use that to go back to the source because it's symmetric. And so for that purpose, we have this S bit here that's set into the route request instance. And so for when the S bit continues to be true, as long as it's true, that means that the packet is still following symmetric links. Yes, question, Emmanuel?
Yeah, so Emmanuel Bocelli, do I understand correctly that if this S bit is set, then basically it functions more or less like RFC 6997? Or like
no, because we want to get rid of this address vector requirement.
Okay. And if it's not set, then you create two trees temporarily, right?
And I remember that you were a co-author of 6997.
Yeah, I'm trying to understand.
Okay, thank you. So I hope you like it. And in the option, we of course include the IPv6 address of the target node, and also from AODV as a way to discard stale control messages. We include the sequence number. This is pretty much modeled on the way that AODV handles sequence numbers as well. So I mentioned this is just a pictorial representation of using the symmetric bit. So here we have perhaps a path for the route request to go from the source to the destination, and the entire way through the symmetric bit stays set. So what that means then with the route reply is just unicast along the same path back towards the source. And I think that's the entire content of what this says here. But for asymmetric, so for instance, if you look at the illustration, this bit is set pretty well to be symmetric until something happens here. And then this particular route request, this is all, by the way, this is a few messages out of the entire multicast route request that's going towards the target node. But here, this link is no longer symmetric, so the bit is turned off, and that means that when the destination gets it, it does not use the unicast route reply possibility. It instead multicasts using a separate instance of the DODAG to find a different path back from to the source. So this is this more. I think I've already said everything here. If the symmetric bit is set, then the route reply is unicast, and the source will receive it as a unicast. If the symmetric bit is turned off, then the instance is multicast, and then the source will receive it as a multicast and know that and by the way, well, and then it will know that the routing is asymmetric. So so I guess I showed a picture of the route request option here. So in the route reply option, we just really need to put in the destination sequence number. And we have a G bit here, which was, this design was developed from, in AODV was a gratuitous route reply. So what with the, let's see if I go back to my picture, I think. Let's say, for instance, that this device here had complete information about route to the destination. Then it could actually sort of intercept the route request and say, I have a route, and here is its metric or other information needed, and then unicast that directly back to the source, assuming that its route is, for instance, symmetric towards the destination. So exactly the way that this gratuitous route reply sits in the RIPL, we've talked about this a bit, but it's a pretty good opportunity to reduce the amount of signaling. And again, this is going under the theory that signaling in wireless networks is to be reduced to the maximum amount possible. So, so that's it. Be happy to take questions, and if anybody would read the draft and give us feedback, that'd be greatly appreciated. That's it. Oops, I did the wrong thing.
It's okay. I can do it, don't worry.
Oh, there you go. Questions?
Time for one question. Yes? No.
Okay.
Okay,
Next
thank
one.
you very
Thank you
much.
very much, Charlie.
Okay, thank you. We'll come back to the mailing list to see if this work should be continued in the working group or not. We don't do it now, okay?
I'm Rahul Jadhav from Huawei, and this draft talks about the route invalidation problems in the RIPL, and it tries to explain the characteristics of the current NOPAD DAO messaging, and it's a problem statement draft, so it doesn't talk about the solution. It kind of explains the requirements that should be for the possible solution. So I'll try to quickly go through this. NP DAO, NOPAD DAO is the message used to invalidate the route with a lifetime of 0. And it's important because in a bigger in a constrained network, it might not be possible to have, it'll be difficult to afford to have stale entries. So what are the problems with the existing NP DAO, or what are the current characteristic of the current NP DAO signaling? So if you can see, once the child node switches the path from the existing parent to its new parent, the NOPAD DAO messaging happens on the previous path. So it's a given that the previous path is definitely not an optimal path for that kind of signaling. So you end up having a less efficient NOPAD DAO messaging. In case of a permanent link failure on the previous link, the NOPAD DAO messaging simply won't work. Because of this, one of the second things is the dependent nodes. Node E and F, there is no NOPAD DAO, there is no provision of sending a NOPAD DAO on behalf of E and F. The P2P traffic is impacted, may get impacted if there is a P2P traffic in the previous subdo DAG. Third, the NOPAD DAO and the DAO takes a different path. So it is possible, these are asynchronous operations. So it is possible that the NOPAD DAO reaches all the way to the border router, invalidates the route, and the new DAO, while the node is switching the parent, has still not reached the border router. So it might as well result in route downtime. So we try to check. In fact, thanks Sung for pointing this out. You know, there is a provision in our RIPL already, which tries to state how to handle the situation. But it's sort of vaguely stated. It says that a packet can be sent in the sub DUDAC to clear the route, to clear the state of in the previous nodes. One of the main objective of the update for this draft is to clarify this stand. So one of the, we received several comments, comments from Sank, comment from Pascal about that the node B would be in a position to detect failure to the node D and then generate a notepad DAO upward. So that is a possibility. So there are two things. The two things I need to highlight here. In which case can B detect the failure, link failure there, and secondly, even if it is possible to detect the link failure, what is the possible set of operations possible, and whether there can be an NP DAO can be generated by two different nodes, because there is some state information which is available only with the node D, which is possibly not available with node B. So this particular slide gives three scenarios where the detection works. So let's say, for example, there is a P2P traffic from node J to D or E or F for that matter, then node B would be able to detect that there is a link failure here, because obviously it will try to route the packet from B to D and it will fail. Or second, if the parent node B has some explicit detection for child node reachability, which is seldom done in constrained node. Remember, upward it is possible. A parent node might have lots of child nodes. It might be in the range of 50s or 100s. So doing that kind of probing might not necessarily be possible. Third, in case of sleepy node, such detection might not be completely feasible at all. Having said that, let's say for the sake of this discussion that it is possible for node B to detect the link failure. In that case, what are the possible options with node B? So we can see that node B has the previous state information stored in the form of path sequence. So path sequence is a 8-bit number which states the latest state of DAO information. So it is there to not accept the stale information or the stale DAOs. So in that case, B from its previous DAO messaging will have the path sequence number stored, which is X, let's say for example. So when node D switches from B to C, and when B detects the link failure here, there are two possibilities. One is to use the path sequence as it is, or to increment the path sequence and send it. If in case it uses the same path sequence, then G and A are going to drop the notepad DAO, because the sequence number is same or equal to, less than or equal to, then it gets dropped. In case it updates the path sequence number to express1 and sends it above, then GA will accept it, BR will also accept it. But then eventually when node D decides to send the DAO with the same path sequence number, because this path sequence number is not shared, then in that case, then this DAO won't take into effect on A and border router, thus resulting in route downtime. So this draft essentially talks about these characteristics and puts up a requirement in the form of a possible technical solution which can solve these problems. One of this was presented in IETF 95 as well, and there's one more addition here, that if possible, the new mechanism technical solution should not add on to any additional memory requirement for NPDAO messaging. Yeah, that's all from myself. Any questions?
Any questions? Yes.
So could you go back to the picture that shows where you were talking about that, and you're talking about whether to increment the path sequence number or not? Right. So what if B increments it by 1, but the condition for changing parents requires that you increment it by 2?
But then this is something which is not stated in the RFC first, and still even if we do that, there is a possibility that node D tries to switch through path C, but finally it couldn't get the DAO through this. Let's say it results in link failure, in which case it will try to still try to change the parent. Let's say one more route is available here. let's say this attempt failed, it will try to some other parent, in which case the sequence number will be x plus 2. So even that won't come into effect.
It seems like there's got to be a way to make it work, but I'll have to think about it.
Sure, sure, that will be great to have some feedback.
Other questions? No. The working group adoption we will do on the mailing list.
All right.
Yep. Okay.
Thank you very much.
Thank you. Okay, then we are now on the last discussion point of for this meeting. It's the role charter. The role charter has been discussed quite extensively already on the mailing list. We are very grateful for all the comments we got and all the wording that has been done. There has been some other additional comments about the length of the charter, also about all the historical information. So we have reduced the charter size even more, and so I'd like to see some of the text now. So see if you can find yourself in that. So there's still the original text. Low power and lossy networks are made up of embedded symbiosis, etc. They're interconnected by a variety of links, etc. So that is still very old text, which has all been there. Then we have, generally speaking, logical LLNs are characterized as follows, but not limited to. Has anybody additional comments on those points that we have here? So operators in hard state, bound state, optimized for saving energy. Traffic parties are not unicast flows, mostly. Yes, Karsten.
The term is defined in the RFC. There is a role terminology draft.
Yes.
Just cite that.
Is there?
Ah, yeah, that will be a
As
good
mentioned
question.
at the beginning.
Yeah.
No.
So just strike all that nonsense.
Thank you. Anybody agrees? It will be even shorter, our charter. But the information density has gone up, actually. Yeah, next one. So then the historical part has been reduced. We now quote the RFCs which say about what the requirements are, so differentiate this group from other groups. And we have focused on routing social areas for connected home building and urban sensor. We know this, but I think that it might be interesting for people who are for the retail charter for the first time and not all the seasoned people we are here. It has developed a protocol that takes into various aspects, including high reliability, etc. So it just sets the scene of what we want to do. Anybody, any remarks about that? Cite an RFC which tells this? No? Yep. Okay. The working group continues to focus on routing issues for LLN to maintain, improve, and streamline the protocols developed by the working group, including our Ripple and MIPL. This was a key phrase, and maybe there are some comments on that.
So if there were interest in, for instance, the AODV Ripple draft, that would fall under the general heading of improving and streamlining the protocols for Ripple, for instance.
Yep.
That would be a possibility.
Yep. Okay. Yep.
Thank you.
Pascal here. We've done P2P Ripple as an experimental, so obviously this group is supposed to produce the standard track for it.
Okay. Any other? Yeah. Oh, please. There is an RFC coming. No.
No, actually there is a RFC, but was that experiment successful?
Yeah.
I don't know. So it was a genuine question.
What was the question?
Yeah, so I can repeat the question.
Pascal said we had an experimental draft called P2P Ripple. And now I would like to hear whether the experiment was successful.
And I think we still need a little more experimental data to call success or failure. I mean, we have some tests, we have some implementation, we have people that played with it. Schenk is one of them. Yeah, I guess it would be good to play with that a little more. Maybe play with Charlie's proposal and come up with some conclusions as to like how to go forward with standard track document.
So acquire additional statistics of Ripple P2P is an item.
But please, it's not my proposal. It's Satish and Anand, not the co-authors. I was actually a late addition to the team. So.
Oh, yeah. Sorry, I was just like, putting a pointer. I'm not saying that it's your.
Pascal here. If we keep the discussion to whether this work belongs or not, I mean, since we had the experiment or whether it's good or not, we need to continue doing this.
Okay.
It's part of what we do.
Yep. Oh, so then there's some text about coordinate closing with workgroups in other areas which constrain networks, 6LoW, up with core, and also with we will align with the 6-man and beer. I hope the pronunciation is correct. And NetMod working group. Yeah. Any suggestions, Manet?
I'd suggest you add Manet
to
the list. And specifically regarding the multicast work.
Absolutely.
That's what we're focusing on right now.
Yeah. Okay, very good. Thank you. So then we have a set of work items which are not the milestones in individual drafts. So we hope that they are actually general enough. So we have guidance in the use of in IPv6 encapsulation. So the working group last call will be done together with 6LoW. So we have heard some about that. The compression and the IP headers in the 6LoWPAN adaptation layer core context also coordinated with 6LoW. Yeah. Automate accession, that was last one, forwarders to reduce message replication. Then I think it's important to do data models for Ripple and Maple for the management, but usually there is very little interest in the working group to do this. So I've written it down. I think it's important, but I hope that there will be some collaboration here.
My personal hope would be that stopping to do it in MIP2 and doing it in Yang might decrease the repulsion.
This is done in Yang 2 1.1, you mean? Is it done Yang 1.1? It's not SMI. It is, yeah. Okay. Okay, so alternative multicast algorithms is the beer forwarding. We thought it was interesting, so we want to keep that in. Yeah, we'll discuss it later on the mailings, but if there are any strong feelings or alternatives mentioned, then I'd like to hear that. Oh.
Well, it's only an example, the way it is phrased, but specifically beer forwarding is a very specific way of doing things, and this is for highly managed networks. So it may
yes, but I think it will also probably be on the size of the network that you may make choices, and this may actually initiate maybe other multicast work where we look at different types of network.
Maybe just instead of things such as something like C or C also.
C, okay. Yes.
Hi, Alberto Rutana, Routing AD. I actually agree with Carson over there that sort of points in that direction, and from your presentation, maybe that's not the direction you're going to go.
Yeah.
So I would even avoid saying anything. Just say alternative multicast algorithms or whatever, and then that way you can do whatever you want.
Okay. Well, yeah.
And the only other net that I have is up there where it says beer working group. Of course, take that out and put PIM. Yes. So in case you guys don't know, PIM doesn't work on PIM anymore.
No.
PIM is now called Protocols for Internet Multicast. So we changed the working group name, recharted the whole thing, and so it's not just PIM, it's Protocols for Internet Multicast.
Okay.
We just kept the same name, so it would be easier for everyone to get confused. Thanks.
Okay. Thank you. Thanks. Always enlightening. Then there was the last one, which is method to improve or correct the current Ripple control message behavior. For example, DIS and no pass DAO. Yep. Anyone wants to add to that? No. Then we are 1 minute for closing time. Oh. Good.
Hi, Michael Richardson. I forgot to ask the working group whether or not we should assume 2460 BIS or not for use of RPL.
You're beyond me.
Right? So all the changes I talked about that changed, well, that's not necessarily, you know, I can't assume that 6-man will change what they said. They seem to be doing it, but essentially it amounts to, do we go ahead with what we had, or do we wait for them to change their mind, clearly change their mind? And I think those are the two choices.
I must put my chair off here, and I say I would do the 6520, etc. bis.
Yes,
would, yeah.
so much nicer. Yes, it would be the desire, but it's, the point is that clearly we would have to wait. Yes.
Pascal here. Well, they already gave us a date for last call. They passed through first last call, so it's not a matter of waiting years, right? It's going to be very soon. So, yes, exactly. We can wait.
Yeah. Thank you, Michael.
Then thank you very much. No? No, please. The milestones will be very deep. Yes, okay.
For the meeting today, we see that there is support or interest in EUDV repeal, so we need to add a work item for that here, right? We are going to send for in the mailing list the updated version. Yeah. Okay, makes sense.
Fine, then this is the end of the blue lists, please. And for the milestones, we want to export that to the mailing list and get some more information about that if people want to work on those items and then see that we put the milestones in. Okay?
I'm sorry,
Yes,
Pascal.
Pascal?
You seem to imply that those things will be adopted. It's not.
No, that's just what I try to say. It is not what I say that we will be adopted, but I think what I wanted to ask on the mailing list, what the people think on the diverse subjects and drafts which have been done. And if there is seemingly enough interest and people think it is too believable work which is done, then we will cite them as a mailing list, and we have the possibility, as a milestone, and we have the possibilities then when other work becomes more mature or interested to add them to the milestones without changing the actual charter. Is that okay? Fine.
We are done.
For me, we are done if the blue sheets are returned.
Okay, thank you very much.
Nobody goes home before.
Where are the blue sheets? Okay.